Welcome. In this lecture we will be looking at the finite element method, and in particular the Galerkin finite element method. So section 6.2 of the book. So some problems have a formulation in terms of a minimization problem, while others have not. In the latter case, we derive a weak formulation starting from the PDE. Starting from the PDE, or in general system of PDEs. So we looked at the Ritz and Ritz-Gallerkin method so far, where we started with a integral form which was given by the minimization problem of the PDE. Now we will start from the PDE and derive an integral formulation, but it's not in the form of a minimization problem. And then we again substitute the finite element expansion in terms of a compact set of basis functions. We have to introduce test functions, and there's in principle a difference with the minimization problem, and in doing so we get the final discretization. So let's look at the Poisson equation in 1D, in one spatial dimension. That's really an ODE, but it's just the simplest case. So that is minus d squared u dx squared is f of x, with u naught is a and du dx in x is 1 is b. So this is 6.2.1. This is 6.2.2. With the domain x in 0, 1 and the variable or unknown u of x. F of x is a given function. Now, we, just as an aside, in an exercise, show that 6.2.1 satisfies a minimization problem. In our essence we already did that, but you can check that. where the answer is minimum of u in the set of allowable functions which are sufficiently smooth. The integral of half the ux squared minus u of x f of x dx. And sigma was set of functions u sufficiently smooth and u of naught is a. So, issue of the Ritz method is the choice of basis functions. And test functions. Within the Ritz method, the test and basis functions are essentially the same. Basic properties must be satisfied. That is, we need a sufficient number of derivatives and boundary conditions. It needs to fit the boundary conditions, fit to certain boundary conditions, I should say, etc. So, on the previous page, I started with this aspect, and this is really from chapter 7. Here I will continue with the minimization problem, and then later we will look at this equation purely from starting with the PDE. But for now I actually follow the minimization problem. So what about these basis functions? We look at the setup of the basis functions. We divide omega, which is the domain from 0 to 1, in subintervals. In subintervals or elements. These are the finite elements. And in 1D these are rods. So here is naught, here is x is 1, and then we have the various elements. So this is element E1, this is x0, x1, x2, E2, all the way till En. This could say be and this is then xn, and this is xn minus 1. So this concerns the numbering. If you would number the first element to be E0, then the numbering slightly shifts. So as long as you define it, that's fine. The solution U of x is approximated as the UH of x by piecewise, generally low order polynomials per element, or element wise. So U of x is approximately U tilde of x, probably the notation in the book, or with the U subscript h of x, such that U tilde of 0 is UH of 0 at x is 0 is A. So let's make the sketch. X is 0, x is 1. Let's take piecewise linear ones. This is A. Let's say this is the function. It's piecewise linear. X naught, x1, xn, x naught n minus 1, and that's made up out of, in blue, the basis functions at each node times the value at that node. The basis functions times the value are drawn in blue. So in blue, basis functions at, call this node, say, xk, and this is then value uk at node xk times the value uk at x is xk. In black, the summation of this procedure giving u of h, giving the approximation of u that gives uh of x. So in black is indeed the sum of these two blue pieces in each element, because it's linear. You exactly see that it matches up. That makes that u of x is sum k is 0 to n of this u of k times phi k of x. This is the values at x is xk, and this is the basis function in the expansion. Often this is written as UH is UK phi k of x, because we use the Einstein summation convention. So U of x is UK far, because with the transformation convention use repeated indices, and then you somewhere have to say it runs from 0 to n. So we take UH as linear, piecewise linear, as piecewise linear approximation of u of x, of u. Hence, this approximation is not C1 on the interval 0, 1. That is, its derivatives are not continuous. First, derivative not continuous. But u of h is only continuous on the interval 0, 1. However, the integral was 6.2.2, which I didn't number, so let's number that. Was it numbered? This is 6.2.2, so the Ritz integral does stay continuous, because the first interval is continuous in each is constant in each interval. The integral exists. So the integral stays finite. So I said why that was. Now we can show that u of k of x has the following form. It's a piece in the adjacent element to the left of node k, and a piece, wide linear piece, basis function part in x is xk minus 1 go xk. So that's in the part where, actually it shouldn't be uk, it should be so that's in the part xk minus 1 xk. So here we have uk minus 1, and here this is node uk. So u of h of k is x minus xk over xk minus 1 x minus xk. uk plus x minus xk minus 1 divided by xk minus xk minus 1 u of k. Well, we can look at this. If we take x is xk, if we take x is xk, then this vanishes, and we are xk here, this becomes 1, and we land in value in uk. If on the other hand we have r in xk minus 1, then this factor becomes 1. And this factor becomes 0. So, so we land up in uk minus 1. So this is 0, this is 1 there. So let's sketch that. So the first part, xk minus x divided by xk minus 1 is this part. The second bit is x minus xk minus 1 over xk minus xk minus 1, which is this part, because it has a positive incline. So it's 0 here, 1 here. 0 here, 1 here. This is in xk minus 1, this is in xk, this is in xk minus 1, this is in xk. So we indeed see, if we take this term in xk, it's 0, that's what's drawn. If we take it in xk minus 1, we end up in 1. Likewise, in this term, if we are at xk, we are at value 1. If we take it at xk minus 1, its value is 0. So drawn on one element, xk minus 1, so element ek, that is element ek. Is that element ek? No, I'm lost in count. 1, 2, that's ak minus 1. So you have to be careful. Then it looks like we have two pieces. This is one piece, that's this piece. I'm marking it in blue. So this piece is, this piece is in blue. The other piece will make red. In red, this piece is in red. So it's value 1 here, value 0 here. So those are the piecewise linear bits which we drew here in element ek minus 1. So this is element ek minus 1 and this is element ek. Let's check if that was indeed the case. Yes. E2 element ek was from, I do that incorrectly. The count, so no, it's correct. That's correct, yes. It's correct, right? E2 was, no, E2, this is, always goes wrong. I have to carefully number this. This is E1, this is E1, and then the K is, the X1 is on the right. Yeah, now it's correct. Did not mess it up there. No. And I said, in which element was this? This was in element ek then. So I have to be careful, it's in element ek. These are actually first order Lagrange polynomials. So we can name them Lk minus 1, x is x minus xk over xk minus 1 minus xk, and Lkx is x minus xk minus 1 is the other one. Xk minus xk minus 1. Yeah, so this one has the negative slope because in the denominator, denominator is, am I saying it right? Is negative. Is it right? Am I saying it no, right? Is that right? Yes, it's x, yes. I would swap it, but you can rework it. So in another language we can say UH of x is LK minus 1 x, that polynomial, times UK minus 1 plus LK of x UK. So LK minus 1 and LK are linear in element EK, and LJ at xi is the Kronecker delta sum symbol delta ij, so which is 0 for I is not equal to j, is 1 for I is j, with ij runs here from k minus 1 to k. So globally, so on omega is from 0 to 1, our domain, we get UH of x is UK phi phi k of x, where globally we have here, say, node xk, node xk plus 1, xk minus 1. We have here the two piecewise linear bits which comprise the basis function, which is 1 in the node and 0 at the two adjacent nodes. So in multi-dimensions it's essential, but in finite elements we generally use reference coordinates to define these basis functions, and we don't use absolute coordinates like in the Lagrange polynomials. So in multi-dimensions finite element methods use reference coordinates. And with these coordinates are coordinate transformation with x transformed to x of xi, with xi, say, in reference interval minus 1, 1. So for 0, 1 it sounds a bit silly, but if you go from A to B or have a 2D domain, it isn't. And that's done such that standard quadrature rules can be used. See book, see the notes I put online on finite elements. So let's define x of xi. That is half 1 plus xi xk plus half 1 minus xi xk xi minus xk minus 1, xi in a set minus 1, 1. So we see that that's true. If we take xi is 1, this is 0, and we land up in xk. If we take xi as minus 1, this is 0, and we end up in xk minus 1. So it's a mapping. And these are in effect the two basis functions which we already encountered earlier. So, so we check. So we have xk minus 1 to xk, that interval, and this is x, that interval maps to minus 1, 0, 1, and this 1, 0, 1, and this is xi. So before we had these basis functions which look like this, 0 here and 1 here. Now we get the basis functions which look like this again. 1 here, 0 there, but it's 0 at minus this one. This one is 0 at minus 1 and 1 at 1. This one is 0 at 1 and 1 at minus 1. So this one then is half 1 plus xi, right? Because for xi is 1, it's 1. For xi is minus 1, it's... And this one, put it in blue, this piece is half 1 minus xi. So that's the advantage. So now we note that. So we have half 1 plus or minus xi as the basis functions. So we note that, and we have, let me repeat it, x of xi is half 1 plus xi xk plus half 1 minus xi xk minus 1. So we note then that the x d xi, we need it as Jacobian, is xk minus xk minus 1 divided by 2. Simply take the derivative of these two terms, then we get that expression. And if we take the inverse, then this is 2 over xk minus 1, which is 2 over kk, where kk is the length of the element, which is a difference between node xk minus 1. Now Gaussian quadrature is a standard quadrature. An integral from minus 1 to 1 of some function of xi. The xi is approximately f at minus 1 over the square root of 3 plus f at 1 over the square root of 3. So this is an approximation. Sum is k is 1 to 2 of weights wk, which are 1 f of say psi k. So second order, we use the second order Gaussian quadrature, which has weights v1 is w2 is 1, and psi 1 is minus 1 over the square root of 3, and psi 2 is 1 over the square root of 3. It turns out it's exact for quadratic functions, so check that. So check. So look at Wikipedia. Check. You can just do it exact for quadratic functions. So now, given that u of naught is a, and u naught is a, always, we write u, the approximation, as sum is k is naught to n, u k phi k, the basis function. We write that as sum k is 1 to n, so we split off. The k is not case because there we have plus u naught of phi naught of x, which in this case, because of the Dirichlet boundary condition, is a. It's not a. It's not u naught is not an unknown. Then Ritz method is to substitute cross in the integral I of u, and then we already derived that sum k is 1 till n, uk 0 to 1 d phi I dx d phi j d phi k dx. So it's a repeated sum. So since I do the repeated sum, I can leave that. Is 0 to 1 f phi 1 dx phi I dx minus u naught, which is a 0 to 1 d phi 1 d phi I dx d phi naught dx plus b of phi n for I is 1, 2, all the way till n. So this is 6.2.23, and derive the exercises. Derive 6.223 from the finite element expansion here and the Ritz integral by varying the Ritz integral such that it's 0. We already did that, a part of it, but this boundary condition here, you'll have to think about it. Note that I is not from 0 to n, because 0 is a known basis function, and because it's known, this is brought to the other side. Notice that this term only there will only be one term, because there's only overlap when I is 1, because then you get, if this is node 1 and this is node 0 and this is node 1, you only have these two pieces. This is the piece which belongs to phi naught. This is the piece which belongs to phi 1, and therefore the integral is only non-zero in this first element E1. So let's see. So let's rewrite that. U of k U of k 0 to 1 d phi I dx d phi k dx is 0 to 1 f of x phi I dx minus a 0 to 1 d phi I dx d phi I dx d phi naught dx plus b phi I at x is 1. Actually, I have to rewrite that. I don't need it's phi I at 1, which will be phi n at 1 only, and that 1 is actually 1. So now let's define, we have before defined this as SKI. This we have defined as BI, the integral. So this is S0I, and only S01 will be non-zero. So then the structure, general structure is SIK is BI. With did I do that there? Yeah, I runs from yes and I, both I and K run from 1 till N because I already took out the 0 there. The general structure is like this, where SIK is integral 0 to 1 d phi I dx d phi k dx, and BI has everything on the right hand side of that equation, so we just collect it, dx minus a 0 to 1, well, I don't have to write it like that, I can write it as 0 I plus b phi I1. So note that 0I is only non-zero for I is 1, and recall that k comma I is from 1 till n. And phi, note that S not I is only non-zero for I is 1. And note that phi I of at x is 1 is 1 for I is n, and 0 for I is unequal to n. Check this, check. So y. The so I would do here exercise 6.2.10. The general matrix structure of SIK is 1 over h for regular h is xk minus 1. So if it's not a regular mesh, it's the structure slightly more complicated, but it looks like this: 1 minus 1 minus 1 2 minus 1 minus 1 2 minus 1. So that's the Laplace matrix, and then we go all the way here: minus 1 2 minus 1 minus 1 1. But this bit, that's just irritating. What was it? 1 minus 1. So this bit is taken out because this is for I is 0 and this is k is 0, and that part we have taken out. So this is for a regular uniform mesh, for regular or uniform mesh. I stop here. Next will be do this in reference coordinates, and then I will discuss the matrix assembly. So we stop then here. I will be a separate short recording.